Level 1. The Mechatronics Engineering Student. You walk into your first mechatronics lab and realize you're expected to know 3 different engineering disciplines simultaneously: mechanical systems, electrical circuits, and software programming. All integrated, all working together, or in your case, all failing together in ways you don't understand yet. Your first project is building an automated sorting system. Small motors move components along a track. Sensors detect the component type. A microcontroller processes the signal and activates the correct sorting mechanism. Simple in theory, impossible in practice when you're 20 years old and you've never soldered a circuit board in your life. You wire the sensors backward. You blow a motor driver by connecting 12 volts where 5 should go. Your code compiles, but the robot does nothing because you forgot to initialize the GPIO pins. Your lab partner, who somehow already knows all of this, fixes it in 10 minutes. You feel behind. You are behind. Everyone in mechatronics seems to have been building robots since they were 12. You built your first circuit last Tuesday. The coursework hits you from every direction. You take mechanical engineering classes, statics, dynamics, mechanics of materials. You learn how forces act on structures and how materials respond to stress. You take electrical engineering classes, circuit analysis, digital logic, power electronics. You learn Kirchhoff's laws and how transistors work. You take computer science classes, programming in C, Python, beta structures. You learn algorithms and how to structure code. And then you take mechatronics-specific classes where you're supposed to integrate all of it. Design a robotic arm that picks objects with precision. You need mechanical knowledge to design the structure, electrical knowledge to power and control the motors, programming knowledge to write the control algorithms. If any one piece fails, the whole system fails. You spend entire nights debugging whether the problem is mechanical slop, electrical noise, or a software timing issue. Second year, you build a line-following robot for a competition. It should follow a black line on a white surface. The concept is elementary. The execution is not. Your robot follows the line for 3 meters, then veers off completely. You check the sensors. They're reading correctly. You check the motors. They're responding. You check the code. The PID controller gains are wrong. You tune them. The robot still fails. You add more sensors. You rewrite the control logic. You test 50 times. The robot finally completes the course. Then it fails again the next day for completely different reasons. You learn that mechatronics is the art of making multiple systems cooperate when each system wants to fail independently. A mechanical part vibrates and confuses the sensor. An electrical surge resets the microcontroller. A software bug manifests only under specific timing conditions. You become a detective searching for failures at the intersection of disciplines. Third year brings real robotics, inverse kinematics for robot arms. You calculate the joint angles needed to position the end effector at a specific location in 3-dimensional space. The math is complex, the implementation is worse. Your calculated angles are correct, but the robot still doesn't move to the right position because you didn't account for mechanical backlash in the gearboxes. You add compensation. Now it overshoots. You tune the compensation. It works for one position but fails for others. This is mechatronics, making theoretical calculations work in physical reality, where nothing is ideal. You also learn computer vision, teaching robots to see and interpret their environment. You write code that processes camera images, identifies objects, calculates positions. Your robot can identify a red ball in perfect lighting. It completely fails in shadows or when multiple objects are present. You improve the algorithm. You add edge detection, color segmentation, machine learning classification. The robot gets better, but never perfect. Computer vision in the real world means dealing with infinite variations that controlled lab conditions never prepare you for. Senior design project. Your team builds an automated warehouse system. A mobile robot navigates between storage locations, picks items, and delivers them to a packing station. You spend 8 months on this. The mechanical design takes 3 months, the electronics take 2 months, the software takes the entire 8 months because integration never reveals new problems. Your robot works in the lab, Then you demonstrate it for the review panel, and a motor overheats because the duty cycle was too aggressive. You add thermal monitoring. The robot works again. Then the vision system loses tracking because the lighting in the demo room is different. You add adaptive thresholding. The robot completes one successful run. The panel approves your project. You graduate. You have a degree in mechatronics engineering. 4 years of learning that making machines intelligent requires understanding mechanics, electronics, and software equally. 4 years of debugging problems that exist in the space between disciplines. You're ready to build automated systems. You think you're ready, you're not. Level 2, the Junior Mechatronics Engineer. Your first job is at an automation company that builds manufacturing equipment. Your first assignment is integrating a vision-guided robotic cell. The robot picks randomly oriented parts from a bin and places them precisely into a fixture. The mechanical team designed the robot cell. The electrical team designed the control cabinet. The software team wrote the vision algorithm. Your job is making it all work together. You spend 3 weeks troubleshooting why the robot keeps missing picks. The vision system identifies the part location correctly. The robot path planning calculates the correct trajectory, but the robot gripper arrives at the wrong position. You check calibrations, you verify coordinates. You discover the issue is a 2 mm offset in the camera mounting that creates a scaling error in the coordinate transformation. You adjust the mount. The system works. Then you discover it only works for one part orientation. When parts arrive at different angles, the gripper rotation is wrong. You debug the rotation transformation matrix. You find an error in how the vision system reports orientation angles. You fix the code. You test 100 different part orientations. The success rate goes from 40% to 95%. That remaining 5% are edge cases where lighting creates shadows that confuse the vision system. You add supplemental lighting. Success rate hits 98%. Your manager says that's acceptable for production. You learn that perfection isn't the goal. Reliable enough is the goal. You also learn that systems work differently in factories than in labs. A system that runs perfectly for 8 hours in testing fails after 6 hours in production because the factory is 20 degrees hotter and motors overheat. You add cooling fans. A system that works flawlessly on clean parts fails on parts with oil residue because the gripper can't maintain friction. You change to a vacuum gripper. A system that never fails in testing fails randomly in production because electrical noise from nearby welding equipment disrupts sensors. You add shielding and filtering. Every failure teaches you something about the gap between design and deployment. Mechatronics in the real world means accounting for variables that don't exist in textbooks. Temperature, contamination, vibration, electromagnetic interference, operator error, maintenance neglect. Your systems have to survive all of it. Level 3, the Mechatronics Engineer. 4 years into your career and you're designing complete automation systems from scratch. A pharmaceutical company needs an automated inspection system for vials. The vials move on a conveyor at high speed. Cameras inspect each vial for defects. Reject mechanisms remove defective vials. The system has to inspect 200 vials per minute with 0 false negatives, because missing a defective product means patient safety risk. You design the mechanical system, conveyor layout, spacing, reject mechanism, camera mounting. You design the electrical system, motor controls, lighting, sensors, emergency stops. You write the software, image acquisition, defect detection algorithms, conveyor tracking, rejection control. You integrate everything. You test it. The system works at 50 vials per minute. You need 200. You optimize the vision processing. You use faster cameras. You parallelize the computation across multiple processors. You reduce inspection time from 200 milliseconds to 50 milliseconds. The system now handles 200 vials per minute. But the reject mechanism can't keep up. It misses rejects at high speed. You redesign the reject mechanism with faster actuators. Now it works until a vial gets stuck and jams the conveyor. You add jam detection and automatic clearing. The system runs for a week without issues. Then it starts getting false positives because dust accumulates on the camera lens. You add automatic lens cleaning. You run a month-long reliability test. The system performs flawlessly. You deliver the project. The pharmaceutical company is satisfied. Your automation system is now inspecting millions of vials per year, ensuring product quality, protecting patient safety. You built something that matters. Level 4. The Senior Mechatronics Engineer. 8 years of experience, and you're leading the development of an autonomous mobile robot for hospital logistics. The robot navigates hospital corridors, rides elevators, delivers medications and supplies. It has to operate safely around doctors, nurses, patients. It has to navigate dynamic environments where obstacles constantly change. You lead a team of 6 engineers, 2 mechanical, 2 electrical, 2 software. You coordinate the development. The mechanical team designs the robot chassis, suspension, payload compartments. The electrical team designs power systems, motor controllers, sensor integration. The software team develops navigation algorithms, obstacle avoidance, task scheduling. The integration challenges are immense. The navigation system uses LiDAR for mapping and cameras for obstacle detection. You implement sensor fusion algorithms that combine multiple sensor inputs into a coherent environmental model. The robot path planning has to be smooth enough to not disturb fragile cargo, but fast enough to meet delivery schedules. You tune the motion controllers for weeks to find the right balance. Safety is critical. The robot operates in spaces with vulnerable people. You implement multiple safety layers, emergency stop systems, collision avoidance, safe speed limits in crowded areas. You run thousands of test scenarios, robot encountering people in corridors, navigating around wheelchairs, stopping for rushing medical staff. Every scenario has to result in safe behavior. You also implement fleet management. Multiple robots operating simultaneously need to coordinate to avoid congestion. You develop scheduling algorithms that assign tasks efficiently and route planning that prevents robots from blocking each other. The system goes live with 5 robots serving a 400-bed hospital. Within 6 months, they're completing 300 deliveries per day. Staff satisfaction increases because they spend less time on logistics and more time on patient care. You created technology that improves healthcare delivery. Level 5. The Principal Mechatronics Engineer. 12 years into your career and you're the technical authority on advanced robotic systems. A manufacturing client wants to implement collaborative robots on an assembly line. Cobots that work directly alongside human workers without safety cages. The technical challenges are significant. The robots need sophisticated force sensing to detect contact with humans. They need vision systems to track human positions. They need control algorithms that ensure they never apply dangerous forces. You architect the complete system. You select industrial collaborative robots with built-in force-torque sensors. You design custom end effectors for the specific assembly tasks. You integrate vision systems that monitor the workspace in real time. You develop safety-certified control software that implements multiple protective layers. The most challenging part is the human-robot interaction. The robots need to be predictable so workers trust them. They need to be responsive so workers can guide them physically. They need to be productive enough to justify the investment. You spend months tuning the robot behaviors, testing with actual assembly workers, incorporating their feedback. You implement hand guiding where workers can push the robot to teach new motions. You add intuitive status indicators so workers always know what the robot is doing. The cobot system deploys across 3 assembly lines. Production efficiency increases by 30%. Worker injury rates decrease because robots handle the repetitive strain tasks. Workers report higher job satisfaction because they do skilled assembly while robots do heavy lifting. You transformed manufacturing through intelligent automation. Level 6. The Engineering Manager. 15 years in and you've transitioned to managing the Mechatronics Engineering Department. 20 engineers working on multiple automation projects simultaneously. You're responsible for project delivery, resource allocation, technical direction, and hiring. Management means different challenges. You're coordinating projects with competing resource needs. You're making decisions about which technologies to invest in. You're handling personnel issues that have no technical solutions. An experienced engineer is frustrated because a junior engineer got promoted to project lead. You have difficult conversations about performance expectations and career paths. You're also the interface between engineering and business. Executives want to know why projects are delayed or over budget. Clients want to understand technical limitations. Your job is translating between technical reality and business expectations. A client wants features that would compromise safety. You explain why that's unacceptable and propose alternatives that meet their goals safely. But you also see your team deliver impressive work. The autonomous inventory system they designed is operating in 6 warehouses. The quality inspection system caught a defect that would have resulted in a product recall. The robotic surgery assistant is helping surgeons perform minimally invasive procedures. Your team is building technology that matters. Level 7. The Director of Robotics and Automation. 20 years of experience and you're directing robotics and automation for the entire company. You set the technical strategy, which emerging technologies to pursue, which markets to enter, which research partnerships to establish. You make decisions about the company's future. Do we develop proprietary AI algorithms or license existing solutions? Do we focus on industrial automation or expand into service robotics? Do we invest in autonomous vehicles or medical robotics? These choices determine the company's direction for the next decade. You also represent the company in the broader robotics community. You speak at conferences, you collaborate with universities on research, you contribute to developing industry standards for robot safety and interoperability. Level 8. The Vice President of Engineering. You've worked in Mechatronics for 25 years. You're the VP of Engineering. You oversee the entire engineering organization. You report to the CEO. You make decisions about acquisitions, partnerships, and strategic direction. But you remember being the confused student who wired sensors backwards. You remember the line-following robot that inexplicably failed. You remember every debugging session that taught you how mechanical, electrical, and software systems interact. Somewhere right now, a mechatronics student is struggling to make 3 disciplines cooperate. They're wondering if they'll ever understand how it all fits together. They will. They'll learn that mechatronics is about integration, about making diverse systems work as one, about solving problems that exist in the spaces between traditional engineering fields. They'll build robots that manufacture products, assist surgeons, deliver goods, explore environments. They'll create intelligent machines that sense, decide, and act, just like you did.